Hi, my name is Ayron Gors, and this is my Project 8 presentation for CE570. I've highlighted the goals for this week's project above. As you can see, we are to assume that the composite body of our choice is already of the deformed shape, and I went ahead and just chose what I've been going with for the previous few weeks with my projects of my silo style shape. And then we are to define a symmetric Cauchy stress tensor Sx, and then to compute the tractions using that equation that you can see right here on one of the surfaces of our choosing on that body, and then to verify the total force on that surface of our choice using this equation as defined here. So below I have defined my symmetric Cauchy stress tensor field that will be applied across my composite body. In order to properly implement our Cauchy stress tensor into our MATLAB code, we had to first parameterize the different surfaces and different bodies within our composite body. As you can see, I have my hollow cylinder and my hollow hemisphere defined and their parameterization, and then just plugging in wherever it's x1, x2, and x3 within the symmetric Cauchy stress tensor field, as you can see above there, into their respective locations for each composite body. You can see results in these different tensor fields, or stress tensor fields, as you can see right here, and then the appropriate lines of code that define them within MATLAB. Now I'd just like to highlight a demonstration of my code running. As you can see, this is my Project 8 code, and you can see my definition of my parameterization inputs, and then my definition of my hollow cylinder and its parameterization, and then the added stress tensor, as you can see, coded in right here. And then moving on, you can also see my hollow hemisphere that sits on top of my hollow cylinder with its appropriate parameterization and appropriate code as defined in previous projects. And then the defined Cauchy stress tensor right here. And then for plotting purposes, the stress tensor is seen. And scrolling through the rest of my code, you can see that I haven't hard-coded anything in, so my code is working appropriately. And giving it a quick run, you can see the outputs as shown right here that we will investigate in a further slide, and then also the graph as shown right here. As you can see, my tensor field, my stress tensor field is varying in the z direction, and as you move up the shape, it increases in intensity. Now we're tasked with verifying the total force that's acting on one of the surfaces of our choosing on our composite body, and my surface of choice is the outside cylinder portion of my hollow cylinder, as you can see highlighted in red there. And then once again, you can also see the stress field as defined on the right. And finally, now I'd just like to walk you through my hand calculations for the verification of my force of choice. So as stated previously, I am verifying the forces on the outside perimeter of my hollow cylinder. So in order to do that, I have to first define the normal vector to that surface, and in previous projects I've defined it before, and you can see it right here as cosine theta, sine theta, and 0. And taking my Cauchy stress tensor and multiplying that by the normal forces with respect to the parameterization of my hollow cylinder, you can see results in a traction vector as shown here. And then taking that traction vector and integrating it across the surface parameterization, where it is varying in the z direction and also varying in its orientation in terms of theta. So I am integrating it in terms of theta and z, and plugging in the appropriate R2 value of 20 and H of 12, and working through all its math results in a 0 entry for the E1 location, a 0 entry for the E2 location, and then finally 45,238.934 in the E3 location. And as you can see, as highlighted for my MATLAB output, this very closely matches my total result. So I know that my code is working appropriately. Thank you for watching.